Section: Introduction. In this section, we discuss the growing concern surrounding AI-generated content and its implications for future generative AI models trained on synthetic data. One major worry is model collapse, where future models may fail because they rely too heavily on synthetic data. This issue has gained significant attention in both academia and industry, with notable publications warning that training on AI-generated text can harm model performance, likening it to inbreeding in computer science. We believe that the prevailing narrative about model collapse oversimplifies the scientific claims and assumptions involved. Through our analysis, we identify three key gaps between the current discourse and the actual research. First, we find that model collapse has at least 8 different definitions related to performance degradation in model data feedback loops. This inconsistency leads to confusion and hinders a clear understanding of the future of deep generative models. We argue that specific failure modes should be clearly identified and discussed. Second, we highlight trends in how leading AI labs pre-train models, such as increasing computational power, improving data quality, and using a mix of real and synthetic data. Many studies incorrectly assume that all previous data is discarded after each training cycle, which we believe is unrealistic. Third, we evaluate the literature on model collapse based on the plausibility of their assumptions. We argue that some definitions do not indicate severe outcomes under realistic conditions, while the most alarming predictions often stem from unlikely experimental setups. However, we acknowledge that there are genuine concerns regarding the tails of data distributions that need to be addressed. Overall, we contend that the concept of model collapse has been exaggerated and misrepresented. While synthetic data does present challenges, our findings suggest that many predicted collapse scenarios can be avoided with standard practices in model development. Instead of focusing on unrealistic catastrophic outcomes, we should concentrate on the real issue of diversity collapse that is currently occurring. Our aim is to clarify the scientific discussion around model collapse, suggest best practices for future research, and shift attention towards generating and curating synthetic data that enhances future AI systems while minimizing failure risks. Next, we will outline the various definitions of model collapse, starting with the important point that the literature presents at least 8 distinct definitions based on different aspects of performance degradation. We analyzed 28 key research papers to identify explicit definitions of model collapse, noting that many papers lack clear definitions and often use multiple interpretations, leading to contradictions. Before we explore these definitions, we will establish some common terminology related to model data feedback loops, where we examine a sequence of generative models that are trained on data and produce synthetic data. We can assess the quality of these models in several ways, including population risk, which measures expected loss across the entire real data distribution, and tail risk, which focuses on the expected loss in rare events. We will now delve into the 8 definitions of model collapse, starting with the most straightforward one: a significant and rapid decline in model performance due to synthetic data, often described as catastrophic, though what constitutes catastrophic is frequently left undefined. Section Summary. In this section, we highlight that the term model collapse encompasses at least 8 different definitions related to performance degradation in generative models, leading to confusion and inconsistencies in the literature. We argue that many concerns about model collapse are overstated and can be mitigated through standard practices in model development, while emphasizing the need for clearer definitions and a focus on realistic challenges in synthetic data generation. Section: Intra-paper definitions can cause confusion. In this section, we highlight how varying definitions of model collapse can lead to confusion. The distinctions between these definitions can be subtle, and authors may switch between them throughout their papers. However, model collapse is a technical issue that needs clear definitions for accurate characterization. We refer to a notable previous study to illustrate how easily one can shift between definitions. Our goal is not to criticize this specific work but to show that even a reasonable approach to defining model collapse can significantly affect how results are interpreted. The study we examine provides clear definitions for 2 types of model collapse: early model collapse, where the model starts losing information about the distribution's tails, and late model collapse, where the model mixes different modes of the original distribution, resulting in a final distribution that looks very different from the original. We label these as our definitions 1 and 2, respectively. However, the paper presents results that align with different definitions. In sections 4.2 and 4.3, the authors demonstrate their first definition. We generalize their findings for clarity. They repeatedly fit multivariate Gaussian models to data and sample from these fitted models. Starting with real data from a multivariate Gaussian, they compute the unbiased mean and covariance from the latest data and then generate new synthetic samples based on these parameters. They show that as the model fitting continues indefinitely, the population risk, measured by the expected squared Wasserstein distance between the latest and original Gaussian, diverges. This finding does not align with either of the two initial definitions of model collapse. We wonder if this divergence could be explained by one of the other definitions. The squared Wasserstein distance between two Gaussians includes contributions from both the means and covariances. While the variance may collapse and tails may disappear, these are not the reasons for the population risk diverging. Instead, the divergence occurs because the sequence of means randomly drifts away from the true mean. This example illustrates that a casual reader might overlook that the population risk diverging is not due to the rapid disappearance of data tails or slow entanglement of modes. The same paper also shows how definitions of model collapse can lead to contradictions. In section 5.2, the authors fine-tune language models on synthetic data and find that while the population risk initially rises, it later decreases and stabilizes at a level higher than the original model's risk. They claim that over time, models generate samples that the original model, trained on real data, would likely produce. We believe that according to our definitions, these results indicate that model collapse has not occurred. However, the authors label this as model collapse because later generations trained on synthetic data start producing samples that the original model would never create, leading to a misperception of reality. When a paper shifts definitions without clear acknowledgement, it creates confusion that undermines scientific clarity. Readers interpret results based on the initial definitions, leading to a false impression that all discussed phenomena are the same when they may be fundamentally different. This can result in misattributing causes and effects, as seen in the Gaussian example where the divergence of population risk was wrongly linked to the disappearance of tails instead of mean drift. Such inconsistencies can lead to overgeneralization of results, complicating comparisons across studies and potentially leading to misguided technical responses or policy decisions. Most importantly, when technical concepts like model collapse require precise definitions, unacknowledged shifts hinder the development of a stable framework for interpreting claims, contributing to broader confusion about which issues are significant and how to address them. To further illustrate how different researchers can interpret the same results differently regarding model collapse, we examine a study on a style GAN2 model trained on synthetic data. The authors found that the population risk, measured by Frechet inception distance, doubled by the fifth model fitting iteration and then plateaued. They claimed this indicated model collapse, having implicitly defined model collapse as any increase in population risk. In contrast, another study questioned this conclusion, suggesting that accumulating data actually prevents model collapse rather than just delaying it. This disagreement arose because the second study defined model collapse as a population risk that diverges over time. Thus, even when analyzing the same figure, researchers reached different conclusions due to their differing definitions. Section Summary. In this section, we illustrate how varying definitions of model collapse can lead to confusion and misinterpretation of results, using examples from prior work that demonstrate the implications of shifting definitions. We emphasize that without clear and consistent definitions, researchers may draw conflicting conclusions from the same data, undermining scientific clarity and potentially leading to incorrect technical responses. Section. Stating and adhering to definitions improves clarity and drives progress. In this section, we aim to clarify that stating and adhering to definitions can enhance understanding and foster progress. We are not here to advocate for specific definitions of model collapse or criticize those we disagree with. Instead, we want to highlight that model collapse is complex. Different researchers may have varying opinions on whether it is happening or not, even with the same results. In the appendix, we provide a case study illustrating how differing definitions and methods can lead to confusion in scientific insights. This complexity makes it challenging to fully grasp model collapse, which can be particularly concerning for certain communities. For example, search engines like Google, Bing, and Perplexity could face significant issues if their models are based on inaccurate information, while marginalized groups may suffer more from the loss of real data. By clarifying and consistently using different definitions of model collapse, we can deepen our understanding of its various failure modes and identify preventive actions. Together, these definitions can create a model collapse profile that describes how models deteriorate over time. Research on the risks of synthetic data should clearly indicate which aspects of the model collapse profile are being examined. Our goal is to explore the likely outcomes as we prepare future advanced AI systems using large datasets that mix real and synthetic data. We focus on pre-training because it has significant implications, as highlighted in existing literature, and because mistakes in this phase can be very costly. We identify several trends in the current pre-training practices of advanced AI systems. 1. Increasing pre-training compute. The amount of computational power used for pre-training is rapidly growing. For instance, Meta's Llama models have seen a jump from 2,000 GPUs for Llama 1 to 16,000 GPUs for Llama 3. OpenAI has also announced a major initiative to boost compute capacity in the US, with some of that aimed at pre-training. 2. Increasing pre-training data. The volume of data used for pre-training is also on the rise. Meta's Llama models were pre-trained on progressively larger datasets, from 1.4 trillion tokens for Llama 1 to 15 trillion tokens for Llama 3. While the total amount of data will eventually reach a limit, estimates suggest there could be around 1 quadrillion tokens available for language pre-training. 3. Increasing quality of pre-training data. The quality of pre-training data is improving as teams develop better filtering methods. Additionally, the synthetic data generated is becoming more reliable as models advance. 4. Synthetic data accumulating alongside real data. Real data is not discarded after each model training. Instead, synthetic data is generated and added to existing real and synthetic data. 5. Decreasing proportion of real data. The share of real data compared to the total data, real plus synthetic, is declining. However, it remains uncertain whether this share will eventually reach zero. We believe that researchers and policymakers interested in the societal impacts of model collapse should focus on studies that adhere closely to these conditions, keeping in mind that computational limits may affect research. Next, we discuss key considerations regarding model data feedback loops. Early research on model collapse assumed a specific way data would be handled. After training, all existing data would be deleted, and the next model would be trained only on the latest synthetic data. This replace paradigm leads to several negative outcomes, such as the loss of real data and increased population risk. However, this assumption is unrealistic. The entire internet is not erased after training, and future models are not solely based on their predecessors' outputs. A more accurate view is that synthetic data accumulates alongside real data, allowing for a broader training base for subsequent models. While some may see these differences as minor, they significantly affect population risk behavior. Research has shown that population risk diverges if data is replaced but remains stable if data accumulates. Another plausible scenario is that both real and synthetic data accumulate, but future models are trained on a smaller, selected portion of this total data. This accumulate subsample approach is a compromise between the replace and accumulate methods, though no analytical theory has yet been established for it. Individual beliefs about the most accurate data handling paradigm can shape perceptions of how model collapse may progress. However, to our knowledge, there has been no connection made between non-population risk-based views of model collapse and assumptions about data propagation, leaving an important question unanswered. Section Summary. In this section, we emphasize the importance of clearly defining model collapse, as differing interpretations can lead to confusion and hinder progress in understanding its multifaceted nature. We also discuss the evolving practices in pre-training AI systems, highlighting trends in compute, data quantity and quality, and the implications of data propagation methods on model performance and societal impacts. Section: Proportion of real data over time. In this section, we discuss the proportion of real data over time. We note that ChatGPT alone generates a tiny fraction of the total words produced by humanity each day. As generative models become more widespread, they could eventually create much more data than humans, which raises important questions about the amount of real data available on the future internet and its impact on model collapse. Some researchers argue that as long as the proportion of real data stays above zero, the risk of population collapse won't significantly increase. However, they also warn that synthetic data can severely degrade future models, and that model collapse can persist even when real and synthetic data are mixed, unless the synthetic data is minimized. We emphasize that understanding these results requires caution. For instance, the conditions mentioned are sufficient but not necessary, meaning model collapse isn't guaranteed if real data remains a small part of the total. Other studies suggest that even if human data becomes a tiny fraction of the internet, the risk of population collapse may not diverge, provided that the rate of AI-generated data doesn't grow too quickly. Given the uncertainty around synthetic data generation, one possible approach is to reserve real training data for future use while it is still plentiful. However, leading AI labs have already gathered such data, so no further action is needed. Next, we address model training assumptions. While some studies claim that models can avoid collapse under certain conditions, we believe it's essential to clearly state the strong technical assumptions that may not be realistic. For example, iterative retraining, where each model starts from the previous one's parameters, is often assumed to prevent collapse. However, this method hasn't been applied to major AI models like GPT-2, GPT-3, or others, making these assumptions far removed from current practices. We also examine data editing as a strategy to mitigate collapse. In this approach, each model iteration generates synthetic data based on previous training targets, with some edits. While some claim this prevents collapse, their proof relies on the assumption that the number of edits decreases consistently, which may not hold true in practice. For instance, training GPT-2 on a specific dataset showed only a slight decline in edits, suggesting that if edits are limited, each generation primarily uses real data. Finally, we consider the timescales of model collapse, which are often overlooked. We describe a theoretical model where drawing data from a distribution leads to a Markov chain that eventually collapses. We can also estimate how many iterations can occur before total collapse happens. If we start with a uniform distribution, the expected number of iterations before collapse is proportional to the logarithm of the number of outcomes. Our simulations support this idea, showing that total collapse is not an immediate threat due to the vast amount of real public text data available. This indicates that we could train many models before noticing any signs of collapse. Understanding the timescale of potential collapse is crucial, and some authors have provided specific rates of collapse for various distributions, noting that while the likelihood of total collapse increases, it does so at a rate that is not practically concerning. Section Summary. In this section, we discuss the critical role of the proportion of real data in preventing model collapse as generative models produce increasing amounts of synthetic data. We highlight that while certain assumptions and strategies are proposed to mitigate collapse, they often rely on unrealistic conditions, and the timescale of potential collapse is slow enough that humanity could train numerous models before significant degradation occurs. Section: Is model collapse a threat? In this section, we explore whether model collapse is a genuine threat. We believe that model collapse is complex, and there isn't a straightforward answer. By averaging results from various studies, we provide our own outlook on model collapse based on different definitions. We conclude that population risk is unlikely to increase dramatically or diverge indefinitely. With the growth in the size and quality of pre-training datasets, we argue that models trained on a mix of synthetic and real data will not face a significant rise in population risk. However, we are uncertain if the amount of real data compared to available data will diminish to almost nothing. While we will lose some real tail data and modes, the extent and speed of this loss remain unclear. The reduction in diversity is a concern, often disproportionately affecting certain subgroups. We do not know how much tail data we will lose or how synthetic data will influence these natural changes. We strongly advocate for more research on strategies to prevent coverage and mode collapse in realistic scenarios. The introduction of synthetic data may alter scaling laws, but we still need to understand how these changes will manifest in real-world conditions. Synthetic data might help alleviate what some researchers call a data bottleneck, but this advantage could come with changes to scaling law parameters. We encourage further investigation into how synthetic data impacts scaling behaviors to better predict future outcomes. While real threats do exist, we believe the common notion that synthetic data from the internet will make future AI models trained on large web datasets ineffective is likely exaggerated. Such failures typically occur under conditions that do not accurately reflect practical applications. We should remain vigilant about subtle shifts in data distributions, like the loss of real tail data, and future research should focus on strategies to mitigate these risks.